Hello, good afternoon. Today I'm going to discuss another important naming reaction. And the name of the reaction, what I'm going to discuss today, is Wolff-Kishner reduction. Okay. So before I discuss Wolff-Kishner reduction, I want to give one clarity about this reaction. If you go to my previous videos, I discussed about Clemmensen reduction there. So if you understand what is Clemmensen reduction, what is a reaction involved, what are the reactants, what are the conditions we maintain there. So if you are familiar with Clemmensen reduction, Wolff-Kishner reduction also follows in the same direction, but with few changes here and there. I'll explain what is the difference you find between Clemmensen reduction and Wolff-Kishner reduction. As I told you, in Clemmensen or Wolff-Kishner reduction, there is one common point. What is that common point? When the carbonyl groups of aldehydes or ketones, okay, they can be converted into corresponding hydrocarbons or methylene groups. Okay, so the output is similar in the case of Wolff-Kishner and Clemmensen. But what is the difference here? The reactants are different. See, in Clemmensen reduction, we converted the carbonyl group into a methylene group or hydrocarbon in the presence of zinc, amalgam, and concentrated HCl. Coming to Wolff-Kishner reduction, I will replace the zinc, amalgam, and concentrated HCl with a strong base like sodium hydroxide or potassium hydroxide or sodium ethoxide. And I'm going to react this carbonyl compound with hydrazones. Okay, so hydrazones will be one of the intermediate product you are going to get in Wolff-Kishner reduction. Okay, now if you see the statement of Wolff-Kishner reduction, it is mainly concerned with reduction of carbonyl groups of aldehydes or ketones into corresponding hydrocarbons or methylene groups by heating their hydrazones at 180 degrees centigrade in the presence of strong base like sodium hydroxide or potassium hydroxide or sodium ethoxide. Okay, so this is a basic statement of Wolff-Kishner reduction. What is the statement here? Reduction of carbonyl groups of aldehydes or ketones into corresponding hydrocarbons or methylene groups by heating their hydrozones at 180 degrees centigrade in the presence of strong base like sodium hydroxide or potassium hydroxide or sodium ethoxide. Okay. So this is what Wolff-Kishner reduction is about. And coming to the general reaction of Wolff-Kishner reduction, so what is a starting compound? You are going to take a carbonyl group. So you can take any carbonyl group of aldehyde or ketone here. So you can take aldehyde or ketone. So initially I will react this aldehyde carbonyl group. So this is your carbonyl group with hydrazine, NH2, NH2. This is the formula for hydrazine. So what will you get here? You will get corresponding hydrozones. So this is hydrazone. At 180 degrees centigrade, you are going to heat this hydrazone in the presence of sodium hydroxide or potassium hydroxide, which is a strong base. You are going to get the hydrocarbon or methylene derivative with evolution of nitrogen gas. Okay, so if you look at this reaction, you can understand how you got hydrozones here. Hydrozones are formed when you heat the carbonyl group of aldehyde or ketone with hydrazine. So you will get hydrozones which can be heated at 180 degrees centigrade to form a methylene derivative or a hydrocarbon derivative plus the evolution of nitrogen gas. Okay. So to understand this basic reaction, we must take the mechanism of Wolff-Kishner reduction so you can understand how the hydrozones are formed, okay, and how we are going to get a methylene group. See, if you see the starting product and the final product, what is the difference? The carbonyl group, the C double bond O, has been converted into CH2, right? So we should understand how this conversion has taken place. Okay. So for this, I'm going to take the mechanism for this Wolff-Kishner reduction. Listen carefully. Okay. So I'm going to erase this statement. And the reaction also, I'm going to erase it because I can accommodate the mechanism comfortably. Right. Now I'll discuss in detail the mechanism for Wolff-Kishner reduction. Please concentrate and listen very, very carefully so you can understand how this conversions are going to take place. Okay. Right. What is our starting compound we have to take? So you have to take your aldehyde, the carbonyl group of aldehyde or ketone, right? So to understand the mechanism, I will write in this way. So thus I'm going to react with hydrazine. What is the formula for hydrazine? NH2, NH2. Okay. So what will happen here now? The two hydrogen atoms of here, okay, the two hydrogen atoms and one oxygen atom will combine together to liberate a water molecule. So this process, what you call this process as? Dehydration. Okay, so what is dehydration? Removal of water molecule. How water molecule is removed here? So the oxygen atom of the carbonyl group and the two hydrogen atoms of the hydrazine combines together to liberate H2O. So what will you get here now? You will get C double bond. Okay, so there is no oxygen, there is no two hydrogen atoms here. So directly you can write nitrogen followed by NH2. And here you will get the alkyl groups R and R dash. Okay, this is nothing but your hydrazone. Okay, so I hope now you can understand how the hydrozones are formed. So hydrozones are formed when the carbonyl group of aldehyde or ketone reacts with hydrazine, the two hydrogen atoms of NH2 and one oxygen atom of the carbonyl group combines to liberate a water molecule. So you're going to get hydrozones. Okay, now this hydrazone I'm going to react with a strong base like sodium hydroxide. So you know when sodium hydroxide dissociates, you will get Na plus and OH minus. Okay. Similarly, you compare the electronegativities between the nitrogen and hydrogen atom. So as nitrogen is more electronegative, the electrons will be attracted towards nitrogen. Therefore, nitrogen will get additional one lone pair of electron. Okay. Therefore, one of the hydrogen atom will get positive charge. So this positively charged hydrogen reacts with negatively charged OH minus to liberate water molecule. So once again, dehydration reaction has taken place here. So what will be the product now? C double bond En single bond. If you remove one hydrogen, you will get only one hydrogen here. Instead of NH2, I'm writing NH. But this nitrogen will have two lone pair of electrons, and here, of course, the alkyl groups will be there. Okay, and you can designate this nitrogen with a negative charge, and this is called as anion of hydrazone. Anion of hydrazone. Now, this anion of hydrazone can undergo rearrangement process. Okay, it will undergo rearrangement. Why? Because see, nitrogen is having one extra lone pair of electron, right? So this negative charge will spread here, and this pi bond will migrate towards carbon atom. So this carbon atom will get negative charge here. So you can write here R carbon R dash. So when you migrate this pi bond towards carbon atom will get lone pair of electron, and you can designate by a negative charge. Moreover, when pi electrons migrates to carbon, okay, you will be left over with a single bond nitrogen, and this negative charge, when it migrates towards this nitrogen, it forms a double bond like this, followed by NH. Now nitrogen will have only one lone pair of electron here. Okay, so the next step will be protonation. What is protonation? Addition of proton or addition of hydrogen atoms. So how can we do this protonation now? Already in previous steps, there is liberation of water molecule. I will use this water here. So water will undergo dissociation to form H plus and OH minus. Okay, so this H plus will migrate towards the carbon, which is having lone pair of electrons. That means carbon can form a new bond with hydrogen atom like this. You will get carbon, hydrogen, followed by nitrogen double bond NH. And of course, you'll be having the two alkyl groups here as usual. Okay, this is called as substituted diimine. Okay, so in the next step, what happens again now? So once again, I'll be using this OH minus here. So you will get R CH, I'll write like this, okay, followed by R dash. Okay, so where from you are getting this OH now? OH is obtained when water is dissociated into H plus and OH minus. Already we have utilized this H plus ion in the protonation step. Now what about this OH minus? So this OH minus I'll be using here. In what way? If you compare the electronegativity between nitrogen and hydrogen atom here, okay, hydrogen will get positive charge. So this positively charged hydrogen and negatively charged OH minus, again, what is liberated here now? Water molecule is eliminated. Again, this step is called as dehydration. Okay, so dehydration is nothing but removal of water molecule. Okay, so you'll get N double bond N. And here nitrogen gets negative charge with two lone pair of electrons. Okay, so as nitrogen is having one extra lone pair of electron, it will move to the next pi bond here, and the lone pair of electrons which are present on this nitrogen will move towards this carbon atom. Okay, so what happens here again now? I'll just erase this. So you will get R CH, and here carbon will get one lone pair of electron with a negative charge. Why carbon is getting lone pair of electron here? Because nitrogen is having one lone pair of electron. So nitrogen electrons will be transferred towards carbon. Okay, and the nitrogen atom which is having two lone pair of electrons, it will be shifted here. So nitrogen can form a triple bond. Okay, so you will get CH and this is carb anion. Okay, so look at here. Actually, nitrogen contains one lone pair of electron, but here you are having two lone pair of electrons. Okay, one lone pair of electron will be shifted towards the pi bond here. So nitrogen can form a triple bond. So therefore, what happens if you break the bond? Okay, so this entire N triple bond N will be liberated in the form of nitrogen. So nitrogen gas will be eliminated out and you will be getting this carbanion. So this carbanion, once again, it will undergo protonation in the present. So H plus will be migrated towards the carbon atom to form R CH2 RH. So this is your methylene derivative. Okay, so where from you are getting this H plus? From water. So when water will undergo dissociation, you will get H plus and OH minus. So this H plus I am using for protonation, where carbon is having one lone pair of electron. So when it donates the electrons for this H plus, a new bond is formed. So instead of CH, you can write CH2. So this is called as methylene derivative. And this is a mechanism of Wolff-Kishner reduction where we converted the carbonyl group of aldehyde or ketone into a methylene derivative, that is CH2, in the presence of hydrazine and a strong base like sodium hydroxide or potassium hydroxide or sodium ethoxide. Either of these you can use for this particular reaction. Okay, and most importantly, if you see the advantages of Wolff-Kishner reduction over Clemmensen reduction, I told you in the beginning of the session, in both the reactions, the end product will be the same, the starting product will be also the same, except the reactants, what you're going to use in the conversion process are different. Okay, but one should understand what is the added advantage of Wolff-Kishner reduction over Clemmensen reduction. As I told you in my previous video, Clemmensen reduction cannot be applied for acid-sensitive compounds because in Clemmensen reduction, you are using concentrated HCl. So because of this high concentration, some compounds will lose their stability. So you cannot perform those acid-sensitive compounds by using Clemmensen reduction process. Okay. And even in Clemmensen reduction, high molecular weight substrates are not preferable. Only low molecular weight substrates can be used in the Clemmensen reduction process. Okay, so coming to Wolff-Kishner reduction, here acid-sensitive and high molecular weight substrates can be used. What is the meaning of this? Suppose if your compound is acid sensitive and your objective is to have convert a carbonyl group into hydrocarbon or methylene derivative, but if concentrated HCl is not supporting you, then immediately shift over to Wolff-Kishner reduction, where the compounds, even though they are acid sensitive, it can withstand. Okay, so their Wolff-Kishner reduction is highly resistant towards your acid sensitive. Even if you use stronger acids also, this is not a big issue here. Okay, so one more thing in Wolff-Kishner reduction, this reduction is only specific for carbonyl groups. Other functional groups of the substrates remain unaffected. This point you have to remember. Okay, so this method of reduction is only specific for carbonyl groups. Other functional groups of the substrates remain unaffected. Okay, so this is all about your Wolff-Kishner reduction and the basic differences between Clemmensen and Wolff-Kishner, followed by the merits or advantages of this reduction reaction. Okay, thank you.